Good evening, everyone, and welcome to tonight's webinar, Mastering Direct Placement Restorative Materials. I'm Dr. John Camisi, private practice dentist in Ithaca, New York, and I apologize for the slight delay in getting started. We wanted to make sure that the sound was right for everyone tonight. We're going to be speaking about direct placement restorative materials, in particular composite, and understanding a little bit about where it's been, where it's going to, and how we're using it, so that this way we've got a better understanding on how to work with this material, which has become such a focal point in all of our practices. It's hard to imagine that this material has been used in dentistry for more than 50 years. And, you know, when I started dentistry 30 years ago, amalgam was the main source of restorative materials for direct placement. Composites were kind of just the beginning phase at that time when I was studying at Northwestern, and it's evolved so remarkably over the years. And I think it's important, in order to get a mastery of anything, is to go back and look at where everything started and how it all began. So tonight we're going to go through a little bit of history, a little bit of science, and then understand what marvelous opportunities we have today. Looking at the chemistry of composites, they're a resin matrix and a filler material together is what makes a composite a composite. Couple that with a coupling agent to enable the adherence of the various fillers that are placed into the resin. An activation system is important, whether it's a chemical or a photochemical activation system. We need plasticizers to enable it to be moldable and injectable and placeable. The monomers and the polymers that go into the overall resin matrix to create these remarkable materials. And looking at different monomer combinations and the copolymers that are created in the overall reaction that goes on within the materials. And then, of course, the evolution of using cross-linked monomers that join these long chains together to improve the overall strength and benefit of the composite materials. When we think back on what Bowen and Bonacor did, and their independent yet important studies that came together over the course of time, with Bowen with his creation and discovery of bisphenol A, bis-GMA materials, and Bonacor with the acid etching of enamel. That's how it all began. And without these two gentlemen, these giants in the sciences of composite restorations, we wouldn't be anywhere we are today. Remembering back when I started, most of the composites were base and catalyst mixtures. You took a dap and dish of one and a dap and dish of the other, and you mixed them together and worked fast to get everything into place before it all set up on you. There was no way of really effectively working with it other than quickly. Mix it up, put it into place, tamp it all down, and hope that you got it adapted really well. Then in the 70s, light curing materials were starting to be introduced, first with UV light, and then eventually into the halogen, and now the LED lights that we use today. And it's remarkable to think that it wasn't until the 1970s that our microfilms were first introduced into the science, and that made a remarkable change as well. Let's look at the resin material itself. Of course, this bis-GMA, which is the base for the composite materials that we use. And in the overall chemistry, the scientists and the manufacturers are adding these dilutants to increase the flow and handling and provide a cross-linkage for improved strength in the material. These diluents are methyl methacrylate, bisphenol dimethacrylate, urethane dimacrylate, and then these cross-linked dilutants of TG-DMA and EG-DMA. These are all important materials in what we do every single day in our composite work. And understanding this basic chemistry helps us move forward as you get to work with it, because understanding what these materials are when you are talking with a manufacturer representative gives you a little bit more insight. So getting into that aspect of knowledge base will help you significantly. Then there's these coupling agents that are added to improve the adherence of these resins to the filler surfaces. You chemically coat the filler surfaces. That increases the overall strength of the material itself. And the interesting part is one of these chemical coating fillers is the silane. Silanes, of course, we know that we use that with a lot of our ceramics when we prepare them for cementation in today's world. But with the silane and the chemistry of composites, they see that there are some problems that develop with it, is that the silanes can age quickly and are very water sensitive. And the common silane agents of the vinyl triethoxysilane and the methacryopropyl, well, that big word is another one of the silane agents. If you can say that, you're in better shape than me. I'm from Brooklyn, and sometimes I can't say those large words, even with the chemistry background. The photoinitiator systems that are available are what make things work today for us. And we have to look at the basics here of the photosensitizers that absorb the light and then transfers energy to the various co-initiator molecules that creates the chemical reaction and the free radicals that set up in the composite setting chemistry. These co-initiators do not absorb the light directly. They are important because they participate in the creation of this reactive molecule in the composite setting. The photoinitiators that we are most commonly used and we're very familiar with are the camphoquinins, the CQs, which require a co-initiator such as an amine to be an efficient photoinitiator system. But then there are also some photoinitiators like the trimethylbenzyl phosphine oxide, the TPOs, which do not require any photoinitiators to be an efficient photoinitiator system. These come in handy, as you'll see in the next slide, because the CQs and the TPOs have different colors and cure at different rates and in different wavelengths. The phenylpropane dione, PPDs, will cure within that 330 to 490 nanometer wavelength with the optimum range of 390. The TPO will cure at the optimum range of 370 nanometers of the wavelength. But the CQs that we most commonly see in most of our initiator systems will cure at the 465 wavelength. That creates some problems because of this yellow color of the CQ. It does create challenges in shade selection. And when you have your highest absorption rates below 400 for the other two initiators, you can run into problems if you're using the wrong wavelength of your light. And that sometimes in the past has been one of the challenges in creating good composite cure, because our lights, if our chemistry in the composites were more TPO or PPD, our lights might not be the correct wavelength. And that's why over the years they've talked about multiple wavelengths within the light curing units that we've used. And we're going to address that in a few moments. Interestingly enough, studies done by LEDs, Vatson, and LEDs, the dental hard tissue, and bonding, the interfacial phenomenon and relating properties. They stated in the study that when you put CQ and PPD together, they can act synergistically to increase monomer conversion of the polymer and reduce the photosensitizer concentration and then improve the color. So this is some of the interesting thing that the chemists are doing in the laboratory to try to reduce that horrific yellow of the CQ and temper it with the PPD color, so that this way we can get a various assortment of shades going on, and also enable the wavelength of the lights that we're using to work a little bit more effectively. And that's one of the things that's been very interesting in the science as we've gone forward. Our curing lights, of course, have been traditionally the halogen, the QTH lights, which had a really wide range of curing light emission from 390 to 510 nanometers. And now today, most of us are using the LEDs, which has a bit of a narrower range of 430 to 510. As you look at the chart on the left, you can see that the LEDs are the low-powered and the high-powered, which are the dotted lines in the middle, and where that range goes as compared to the pack light, which is the solid red line, and the QTH, which is the original halogen light. And you can see that that halogen light spectrum was rather broad, and it could cure most of the materials, whether it was PPD or CQ, very effectively. The TPO, you need a special light typically to get that effectively worked with, and we'll talk about one of those possibilities. If you know that you're working with a composite that has a photoinitiator primarily or composed of partially of TPO, and you want to make sure that you've got things cured. An interesting paper done by Price et al. Called The Effect of Distance on Irradiance and Beam Homogeneity for different LEDs was published back a few years ago in 2011. And it's been worked on a principle that I've been very curious about and has been talking about for a while, in that as you increase the distance of the light from the base of the composite, your energy is going to dissipate. And on top of that, the overall intensity of the light in this study has shown that these various lights over distance, there's a significant change. And the chart on the lower left, you see that you have the fusion in green, blue phase, demi in the dotted red, and the magna lights. And over the course of distance, you see how the effective output of energy decreases from the 1 millimeter all the way to the 9 millimeters of distance. The lights that seemed to do best and kept above the 400 nanometer minimum wavelength necessary were, of course, the fusion, the blue phase, and the demi. Of that, the fusion light, even at 9 millimeters, still gave some really good output of over 1,000 nanometers milliwatts per centimeter squared of energy, and that's been one of the most critical aspects. So when you're looking at energy output, you really do need to know what your light is doing, which is part of a randomized study that I did at my office, and I've been talking about for years. And typically I just showed one light, but now that I have 3 different lights that I've been studying in the office, I figured let's do the test with all 3 lights. And we have the fusion on the left, the radii plus in the center, and the new demi at the right hand side. And you can see right when you have the lights on the aperture, their energy output, the milliwatts per centimeter squared, is quite high. But as you begin to move out, you start to lose energy. At approximately 3 millimeters distance, by putting on a measuring washer into the area, we're able to see that the fusion was able to still maintain around 1720, the radii plus 1470, and the demi lost the most, being at 1110 overall. So, of course, we decided that we needed to push this a little bit further, and we looked at it at about 7 millimeters distance. And again, the fusion and the radii plus and the demi still were doing pretty well, but still that's a lot of energy loss when you looked at it from where it was on the aperture. So the fusion, of course, in this part looked the best of the 3. And then, to be really ridiculous, we decided let's see what it can do at about 12 millimeters distance. Typically we don't have that kind of space from top to bottom of preparation, but it still is important to look at the energy output of the lights that you're working with. And the fusion, of course, had still the best output, with the radii plus coming in second and the demi coming in third. And again, this is a very rudimentary test, but it did give a pretty good indication and did corroborate some of the information done in laboratory by the other paper. What does this all basically mean? That the fusion light by Dent Light is certainly one of the ones that I'm looking at as a workhorse in my office. And interestingly enough, it has a violet light head that you can attach onto replacing your regular curing light that will cure in the 390 to 430 range. So if you're not sure that you're getting full curing, knowing that you have another light head that you can change into to cure the initiator of the TPO in this lower wavelength might just give you a little bit more of a confidence level as you're going on. And I found that extremely interesting to know that one light can have various uses in that aspect. So what's the takeaway of this aspect of mastering your composites? Well, basically, you need to check the energy output of all of your lights. If you don't know what the number as far as the output is, you really don't know what kind of output that you're getting. You can see lights moving up and down on your built-in radiometer on your lights, but does that really give you a quantifiable energy output? You need something that's going to give you a quantifiable energy output. And if your energy isn't sufficient and you're at a specific distance, the further away that you get, the more time you're going to need to your cure in order to be sure to have sufficient curing of your composite. Otherwise, you don't know if you're creating a Tootsie Roll Pop, basically. Hard on the outside, chewy on the inside, which can then help to contribute to sensitivity and premature failure of your composite. So knowing what your energy level and knowing what amount of time that you may need is important. But please remember that if you are adding time, you can also be adding heat to the tooth surface. That heat will, over the course of time, injure the pulp if you're not careful. I know many of you are probably saying, but my LED light doesn't emit heat. It emits quite a bit of heat. If you've ever checked it between your fingertips turning it on, you'll see that there's some heat. And if you really want to know how much heat is being generated, put a bit of composite on your thumbnail. Cure that. Watch the heat start to emerge, and you'll start to understand what I'm talking about. So that's a little fun fact and a fun demonstration that you can do in your own office to identify just how much heat your patients are experiencing, because even though we don't think about it doing that, there is heat being generated. And if that heat becomes too intense, it could cause a bit of pulpal damage. Now let's look at the fillers of the composites. Fillers are necessary to improve the physical properties. They can reduce the shrinkage of the composite upon curing, and they help with the overall composite characteristic. Basically, the fillers are going to determine how polishable or how tough, how wear-resistant these composites are. So your filler material, the surface of the material, the size and shape, the filler load, how much is in there, what modifiers are added, and of course the size and distribution are going to affect the composite characteristics that you're working with. Many of the materials used in our composite as fillers today are of course the strontium glass, barium glass, quartz, borosilicate glass, ceramics of various types, silica, and also pre-polymerized resins, to name just a few. The classification of the fillers and the composites that we use, of course, are based on the shape and size of the filler particles, whether they're irregular or spherical in shape. Spherical, of course, is easier to put into the matrix material of the resin, and the smaller particles can be added to larger so that you get even less shrinkage, less free resin in the composite material when it cures. And of course, it enables a better distribution in that capacity. And if you mix them right, you're going to get a more compactly and tighter and stronger composite material in the manufacturing process. The categories, of course, are the typical ones that we all know: the microfills, the hybrids, the microhybrids, the nanofilled, and the nanohybrids. All of them are based on the particle size overall. And this slide on the right, of course, you get a pretty good understanding and schematic and the overall cross-linkages that go on and how you go from a hybrid to the small particle hybrids to nanofills, midfills, microhybrids, and nanohybrids. These are what our chemists are looking at in laboratory when they're developing these various wonderful materials that you and I work with. And again, if you look at it from a linear scale, as in figure 1, you're having the larger particles and the smaller particles moving from right to left as we're going. And in the lower figure 2, you have the examples of the composite classification based on the filler size. And the middle one is the one that's really the most important. You're looking at the megafill, which is the monster particles inside the resin, the macrofills, which is what I started working with 30 years ago, then the minifills, the microfills, and the nanomicrofills that are going on nowadays. Characteristics are all dependent upon what these filler materials and how they interact in the matrix of the composite itself. The characteristics are going to be that are determined by all of these various items are the coefficient of thermal expansion, the water absorption, surface texture, the radial opacity, the modulus of elasticity, and of course solubility. All of these characteristics are very important day to day when we're working with these composites. Stresses, especially the internal stress that is caused by polymerization shrinkage. That is a big factor that is causing some of the science today to look at this stress that's going on, not only from just the polymerization itself, but also from the shrinkage stress that occurs. And we'll talk about that briefly in a few moments. The internal stress should be and can be reduced by incremental placement. So instead of putting in 4 millimeters with a regular composite, making sure that you put in 2 millimeters at a time. If you're using some of the new bulk fill composites, then of course you will be able to put in a greater amount and have less internal shrinkage, but you still will be developing stress, because stress is a factor of multiple items, such as preparation design, bonding in materials, the overall physical properties of the composites, all of these, the intensity or lack of intensity of your light. They can be reduced, of course, by using stress breakers and liners, such as filled dental adhesives, or my favorite, resin-modified glass ionomer pastes, which in my opinion, to date, seems to reduce stress the most. And if you want to know more about that, previous webinar that I did talks about the reducing shrinkage stress in composites. You'll want to listen to that when you have an opportunity. When we look at the composite selection, of course, the scientific parameters that we looked at is the strength of the restoration, the wear, the color of the restoration, the placement characteristics, how you would be able to combine it with various opacers and tints, how easy it would be to place and shape, how polishable the material would be, and of course, color stability. I'd almost say nowadays when you and I order composite, we're probably looking at, for the most part, shades and probably the overall strength and wear of the restorations. Color stability sometimes is not something that comes to our minds when we're looking and thinking about all this, but maybe we ought to, because if it doesn't hold its color over the course of time, especially in an anterior region, it can really look badly on us at a later date. Ease of placement and shaping, whether or not it's too sticky, if it stays in the preparation, if it molds the way that you need to. Do you need any special instrumentation to make it stay where it is? This is also a personal preference that you have to come to grips with. Some of us like it to be very thick. Some of us like it to flow. There's a benefit to both. You just have to be able to use it in the way that you wish to find that opportunity. Now, we have some advances that are going on. These multifunctional composites with novel microstructures are being developed that you and I are working with today. And there are really some excellent materials that are being developed that I've been working with over the course of time. These materials are tailored via the microstructural design that the scientists are putting together in lab, using this micro and nanostructural levels, they create these new classes of composites which have remarkably improved properties. So, like I said, like what I worked with 30 years ago, the materials that you and I work with now can be so extremely exquisite in their ability to mimic the natural structure. And that's because of these new microstructural entities, the nanotechnology that's been introduced into the science of of the composite chemistry. The nanomaterials basically are structures that are between 0.1 and 100 nanometers in size. They have inclusion of these filler types that improve the physical properties, increase the strength, the polishability, the wear resistance, they improve the aesthetics, and our bond strengths to the bonding agents that we use. Some of these nanostructures are called nanorods, nanofibers, nanospheres, nanotubes, and the most interesting one are the armospheres, these organically modified ceramics. These can all be used to create these biomimetic restorations that will wear and act and be very much as close to the natural tooth structure as we can get in a composite restoration. They not only mimic the physical characteristics of the tooth structure, but in some cases with certain fillers can help facilitate remineralization. And that's some of the really exciting things that I've been seeing in my work over the last several years working with many of the companies. They are developing these really incredible things to help us not only fill a hole in a tooth, but help that material help the tooth protect itself from the advances of new bacterial assaults, acidic assault, that I talk about when I'm on the road and lecturing. These nanotechnology fibers will improve the light scattering, and by doing so, improve the translucency and opalescence of the material. So again, giving it more of a natural appearance. The wear resistance, we can get a higher gloss after finishing and polishing than we ever could, even just 5 years ago, with the materials that we're using today. And because of this high polishability and because of some of the filler materials that are placed into these composites, you can actually reduce the biofilm buildup around the restoration. And we know that a non-polished surface, especially in the interproximal and gingival area of the tooth, is going to be a haven for biofilm buildup and secondary decay and breakdown. So having these materials that can improve that polish, that can improve that resistance to biofilm buildup is extraordinarily important. This leads us to this next section, and a quote that was provided by a representative from the company that we're going to talk about next. The creation of the first low shrinkage, low toxicity composite that works both for anterior and posterior teeth and is compatible with your regular adhesive systems. Now, to say something like that is rather interesting because everybody, most of the companies out there, you need to use their bonding system with their composite. They formulate it as such. For a company to come out and tell you that you can use their composite material with any of your regular adhesive systems is rather gutsy. But in this situation, it works. And the material that we're going to talk about for the remainder of the lecture is called Endurance from Septodon, which is a nanodimer material. This is brand spanking new technology to me. When I started learning about this, I was amazed by what the folks at Septodon have done. This new chemistry that they have created provides incredible physical properties and incredible aesthetics and handling. So what is the nanodimer technology? It's a breakthrough in creating this unique, innovative mix of dimethacrylate monomers together. There is a proprietary monomer based on a dimer acid technology, this DDC-DMA, dimer dicarbamate dimethacrylate, mixed with this EDPADMA, or the ethoxylate dimethacrylate, and this UDMA, the urethane dimethacrylate. this all gives it special properties. The urethane dimethacrylate is interesting to me because I believe that gives it a little bit of its flexural strength that we'll be talking about shortly. That's my suspicion based on the chemistry that I understand. What Endurance does is it can reduce the polymerization shrinkage because it doesn't enable it all to clump together. In the lower diagram, you will see that the material here is all basically fused together in one diagrammatic clump. When the composite cures, there's a single phase of polymerization that basically stiffens the gel of the composite all at once. What Endurance does, which is very, very different, is it creates these various phases and separations, as outlined by the red and blue, that basically enables this to have a little bit more flexure, a little bit less shrinkage, because it's not lumping and clumping together all at once. This is remarkable chemistry, and I haven't seen anything else quite like it out there so far. It creates low volumetric shrinkage because of that phase of curing, those little individual clumps rather than one large clump of curing. Has incredible radiopacity, has a high compressive strength of 319 megapascals, compatible with all bonding agents that are out there. And this is the most important thing. It has a high intraoral monomer conversion of 75%. 75% is remarkable. This optimizes the physical and mechanical properties of this composite material. Looking at this chart, what you will see here is that you've got everybody's in this box, essentially, in which the conversion rate ranges anywhere from 40 to 65 or so % conversion. But when you start to move to higher conversion rates, you get higher shrinkage going on. And that's one of the problems that we have seen is in many of these materials that you and I have been working with, is that we want a higher level of conversion in order to make things stay better in the tooth structure. But as it does that, it creates these stresses, and it really creates a problem with what you and I have been seeing in our restorations, causing the gap formation. What Endurance has done, and what the people at Septidont has done, has created a conversion rate that is very high, 75%, and volumetric shrinkage under 1.5 megapascals. That is unheard of in a lot of different things, and it's really remarkable that you can get both of those in a single material. This increases the biocompatibility also. Because of the unique monomer conversion, you're not going to have high free monomer out in the material, out into the tissue, out into the oral cavity. So you're not going to get that excess. So you're going to have less tissue response and less postoperative sensitivity because of this high conversion rate and this biocompatibility, which, again, I think is absolutely remarkable. Before I started working and looking at this material, I had not heard or been able to find this. So this is quite remarkable. And again, at this chart, as you look at the overall comparatives with many of the very popular materials that are out there, Endurance stands out above the rest. Many of them are really pretty darn good. Again, getting up to almost 65% with the premise as a nano-filled material. But everything else doesn't convert very much. And that can be a problem, especially in patients who may be sensitive. This filler material is also interesting that they're using in here. The nanotechnology used here is the ytterbium fluoride. I've said that better. Nanoparticles and these nanoclusters of this ytterbium fluoride material. Also the barium glass and the silica particles. So all of this creates a very tight filler and a very effective conversion rate of the composite itself. And they've been able to create some great aesthetics because of the filler, because of the conversion. They have 16 shades, Vita shades available, including plus an opaque, an incisal, and a bleach white, and able to get you extraordinary polishability to get a very natural looking material. Good radio opacity, so you can detect it in your radiographs. Non-sticky, easy to place and sculpt. If you're like me, I hate trying to put something in there and it pulls back out on you. Nothing drives me crazier and makes my day much more frustrating than a composite that's sticky. Water absorption and solubility are quite outstanding for endurance. Very, very low water solubility and low water sorption. The lower that the water sorption comes in, the better the color stability. So you can be pretty sure that this product is probably going to give you the long-term results that you're looking for. Compressive strength is quite good. It's up there, only beaten by two other materials, Filtex, Silurane, and Simile. Those are the only two that beat it, but really not by much. Most of the materials out there, you do have, to be perfectly fair, most of the materials out there do have some really wonderfully high compressive strength. But what surprises me, and it keeps me coming back to it, is how endurance continues to be high conversion, high compressive strength, great color stability, great color match overall. Flexural strength is the ability for it to be able to withstand the forces and to help to reduce the composite fracture. And anything over 80 megapascals, according to ISO, is the minimum standard that is necessary. And all of these composites listed here are certainly over the 80, with endurance in the middle of the pack, doing quite nicely at around 120. So it has nice flexural strength as well. So you're not going to get that cracking and chipping that you might otherwise expect to see in other circumstances. Plus, on top of that, you have really wonderful wear resistance, which is quite nice as well. Some examples of work done with endurance. You know, when you fill in an incisal edge on number 9 like that, you really are sometimes asking for trouble, because in this situation, especially looking at the lower incisors there, you know that there's an occlusion situation that's going to keep on popping that thing out. So having something with some decent strength, and of course balancing that occlusion in the front to minimize the forces there, you've got a lot, you're going to have a better result long term. Posteriorly, you're going to get really nice results there too. Getting out the old restorations, making sure you're clearing out the decay. You make life easier and nicer for your patients as you go forward. Not to sit on its laurels, Septodonts decided that they would also create a product specifically for class 3, 4, and 5 restorations, Endurance Crystal, which has an increased translucency, an extreme hydrophobic material for, again, great color stability, long-lasting aesthetics. Again, continuing with the low volumetric shrinkage, improved marginal integrity, and reduced microleakage. That high conversion of the monomer, excellent radiopacity, and again, compatible with all of your bonding materials that are out there. And I love this chart because it shows you the aesthetics, the translucency that you'll be able to get in those areas where you want it. So you can use a nice base dentin color into your restorations and your aesthetic work, and then you can complement it with the translucency of crystal and be able to create a wonderfully aesthetic and a very, very beautiful restoration long term. Interestingly also, some of the working characteristics of crystal is that it's highly thixotropic. That means that the more that you work with it, the more pliable it becomes. So you can really sculpt this material in ways that you may not be able to do with many of the other materials out there. I find that very, very helpful and very, very exciting as well. It's helped with the restorative work that we've been doing and the aesthetics as well, and I think you'll find it to be quite remarkable too. Again, polymerization stress in the tooth structure is very low. Only Venus Diamond is better at this point in time, and then we had this shrinkage, the volumetric shrinkage, also very low because of that overall chemistry of enabling the phases of curing rather than one major bulk phase cure. And, of course, the zero solubility, that's been very important as well. Now, for those of you who are listening, this is something that shocked me, that a company would have a warranty, a guarantee on its product. And when I read this, I was very, very surprised. But I think it says something that Septodont is willing to have you work with them to check this out and to see what they have to do. Because if your composite fractures, cracks, chips, or pits over the covered period of the warranty, any claims submitted, you'll be reimbursed with $100. I've never seen that before. I think that's rather remarkable. I think that it's something to talk with your Septodont representative when you see them, perhaps at the Greater New York meeting, perhaps at any of the other regional meetings that you're going to be with. I think it's something to look at. It's unheard of. I haven't seen any other company ever do anything like this. I don't think it's a stunt. I actually think it's something that they're very sincere because they want to help folks understand what endurance can do for you.